Good evening from the woods of Maine. It is December. It's December 19th, near the equinox of winter. It is cold and going to get extremely cold tonight, down in tonight in the 20s, but we're going below zero over the weekend. And it's the first time we didn't even go below zero last year, which was kind of frightening in my opinion, um, because I mean, we should be going below zero at least once or twice a winter. Um, and it's sort of serendipitous that I'm actually doing this particular part of the talk, because the reality is that mass extinctions all involve one thing in common, and that is climate change. Climate change does it every time, does the trick. It is undeniable. And every one of these mass extinctions I've got lined up here all involve some sort of climate change. And usually it's a rapid one. So I don't need to spell that out any further, where I'm going with that statement, because, you know, even by the standards that these happened, the one that we are inducing is much quicker. So it's something that really needs to be paid attention to, and I will brush over why during this lecture, when I discuss the Permian Extinction Event, because it is really the granddaddy of them all, you know, essentially wiping out 95% of life at that particular time. And, you know, the Permian Extinction, the life forms up until this point in the Permian had basically developed to occupy every niche that we have today. Even the creature designs are similar. Like, you have predators in the form of gorgonopsids that look like lizard-like reptile. I mean, lizard-like lions. They have the same teeth. They have the same structure. Um, they have the same. They're bigger. They're more robust, and they are definitely gnarlier. If you were to come across, if you had a pet lion, and let's just say it was Mufasa, and you came across a gorgonopsid, you're going to lose. They are just bigger, more powerful, and you know, mammals can be very vicious, but you know, they almost pale in comparison to the lack of mercy that you'll see that comes from a reptile. You know, that's why very few people have pet alligators. You know, you can get close to a lion in a zoo, and there are people that have them. I mean, it's probably not a good idea, but you know, you try taming an alligator, man. The brain just isn't as big, and the part of the brain that really focuses on aggression is gigantic in proportion to the rest of it. So, in any case, you know, we also had herbivores like in the savannah, you know, that occupy, you know, grazers, plant eaters, that were obviously the prey of the gorgonopsids. We had very thin, agile, nimble reptiles that are starting to look like, you know, what is going to become dinosaurs. Uh, you know, we're about to really branch here, where the reptile is now going to be the highest form of life, most evolved rather, but we're about to really, you know, make some serious changes when this comes through. Our mammal lineage has already been set up. The gorgonopsid is part of it, and of course the gorgonopsid was a derivative, or rather a descendant of the Dimetrodons, which were also, you know, in our lineage of mammals. And then you go back a little further than that, and you get into a common reptile, and of course you're going to trace it back to the amphibian, which goes back to the fish, and blah blah blah. Anyway, so let's talk about mass extinctions, and we always talk in terms of the big five. Most people know all about the KT. You know, it's been glamorized by Hollywood. It's sexy. It's fun. You know, there's asteroids involved and all this stuff. And let's face it, everybody loves dinosaurs. You want to get a kid in science, show him a volcano and show him dinosaurs, and he's hooked. I am a perfect example of that. Also, then we have the Triassic. Not many people know about that. That is associated with the opening of the Atlantic Ocean. Then, of course, the Permian, which I'm going to discuss in further detail. But before that, we had one in the Devonian. That took out 70% of life at the time. 340 million years ago, yeah, we had some asteroid impacts. We also had rapid cooling. And, you know, this may have been a result of you know, continental position of Gondwana. Gondwana, you know, started moving south over the poles, so maybe that you know, started to more or less cool the climate off. You know, you get glaciation of poles. Well, you know, we noticed that into the Devonian, in the Carboniferous, it still stays warm, but then you get a steady drop, and it stays warm to the Period, but then you get a really steep drop. So, you know, there could be a few things that are associated with the Devonian. It could be a plethora of things. I don't know a lot about that one at this point. I haven't put any time into it yet. I've got other lectures I want to do. But we know that, like, and a very common theme is global cooling, because global cooling takes away water off the continental shelves, and life thrives on the continental shelves. And if it drained the continental shelves, you're going to have some problems. So I'm just going to go as far as that might have been a problem. You know, in the Devonian, life was mostly in the ocean, but, you know, the things were starting to move on land. So one might even say that, you know, this is when the plants kind of started really coming around. So, you know, actually, I'm sorry, the Ordovician was when the plants really started going. And there's a good chance that that rapid cooling from the in the Ordovician one was caused by the arrival of plants. You know, basically breathing carbon dioxide. You know, when you have a land-dwelling plant, you're taking away carbon dioxide. So we also had a rapid cooling event in the Devonian. What it's attributed to, possible volcanic eruptions, asteroid impact, I don't know. But we do know that it affected mostly oceanic life, because there just wasn't a whole lot of things on the land. So we see more of the effects in the ocean. Anyway, on to the Ordovician. The Ordovician had an 85% death rate, really second in command only from the Permian. And this one, I'm fairly certain, had something to do with you know, the arrival of plants. Also, not just plants, but you know, the arrival of things that were attempting to get on land and colonize. So you may have, you know, once this occurred, we know that in the Ordovician, the plants really started to show up, but it's the Silurian when they really get going. But in any case, something like that is going to be starting to suck up oxygen, and it's going to start. You know, you take the oxygen out, and and of course they take the CO2 out, and then give out oxygen. You're going to start, you know, basically oxygen will cool the atmosphere, CO2 will warm it. There could have been other causes about that, but again, we have that falling sea level, and again, if the continents were to be drained, the shelves anyways, you're going to have real problems. I don't know, it says there are chemical reactions affected by the cold. Not 100% what that means, so I'm just going to, you know, again, I'm not on that topic right now. So we're just going to leave those as more or less, you know, I'm fairly unsure what the actual cause was, but something was removing oxygen and probably popping in a lot of carbon dioxide. In any case, so we shall move on. So when we look at the charts of the Big Five here, obviously the biggest divot, or the cliff rather, is right here. And again, I was saying that, you know, you had your number of marine fauna here, families, but you kind of peak out. And why is that? Well, you know, that who knows? But evolution, for some reason, sort of hit in the stock world, they call that resistance. And you know, it sort of like hit this peak here at about 500 families. You had a big dip right here in the Devonian, and of course the end Ordovician had one here. Triassic one doesn't look that big, so maybe it affected land animals more. And of course you had the Cretaceous one here, and this would be much deeper if it was including land animals. So anyway, this is interesting that you have everything's represented here in the early Cambrian. yet you see it kind of stumble along and then drop like everything else, but then it explodes. The Paleozoic ruling life forms also take the big hit, but they sort of continue, creeping along. And of course, the Cambrian take the earliest hit, and then they just pretty much get bombed down to, they the KT extinction more or less takes on. I also want to mention that we talk about the big five, but there's really, we could say that the next one will be the seventh, because there's a lot of speculation now that in the Ediacaran, right around it's 580 to 580 to 5, around 580 to 540. Somewhere in there, right before the Cambrian, there's an extinction event that wipes out most of the Ediacaran biota and a large number of species that exist at that time. The problem was we just don't have the documentation of it in the fossil record. So it's more or less, done through chemistry, and other various means by looking at, carbon ratios and oxygen. It's very, very complex, but that's what they do now. And you can get that out of the rocks. Our technology has come that far. But we had a very nasty one here, back around, around 550 or so. They're just, the species that were living, the Ediacaran biota really got their kick going, and they were doing well, and they lasted about 20 million years, or maybe even 40 million years, and then they got snuffed. So, and not just them, but a bunch of other ones right here at the boundary. So the Neoproterozoic is a very fascinating time. We had the snowball Earth, and then from the snowball Earth came these Ediacaran life forms we call the Ediacaran biota, and they're really they're not so much multi-cell. I mean, they're multi-cell organisms, but not like we are. We are multi-cell, meaning that we have cells within. We have different cells that do different functions and blah blah blah. But they're more advanced. In other words, there's structures within us that have different cells doing different things. But the Ediacaran biota had a couple of different, like, say, appendages or sort of skin areas, if you want to use that term. But instead of that, like, each different area, let's say that there was a pod that stuck out, or a frond, or something like that, or you had the Dickinsonia, which was just like this sort of like round oval thing that we think it might have been the first kind of predator, or at least we do know it's an animal. But parts of it are grooved and parts of it are smooth. So you got two different cells going on there, but they're not operating in the same area. They're operating in different areas. And what these cells did is they just stacked on each other and sort of made themselves bigger, and then became macroscopic. And they're soft-bodied, so the only fossils we see are really impressions in muds and silts and stuff like that. Some sands, but mostly you really kind of need the muds. They're better. So it was like life's first attempt at kind of bringing things together and seeing what, and trying to specialize certain areas of the organism, we'll say. But there was no stomach, there's no mouth, there's no digestive tract, there's no anus, there's no eyes, they're just very simple, probably 3 or 4 different kinds of cells, and they operated together, and they each had their own purpose, and they stacked, and they grew to some size, and they were macroscopic. So, but then they got whacked, and for a while we didn't think any descendants of them made it. But as it turns out, we kind of piecing together that we think that some of their genetic data lives on, and I'm not going to go into it because it's still very speculative. But in any case, those are the mass extinctions. It just gives you an idea of the dents that they put in the marine environment anyway. But look at the cranking of the modern day life forms once you had that extinction. When you brought these down, right, less more, it became less more. So life is a zero-sum game. When something is depleted, something takes its place. And so you can see here it was all Paleozoic. They just killed it. Here modern forms existed and they started growing, but they really took off once these guys took a big die off and started taking less pieces of the pie. All right, on we go. So the late Permian extinction theories. This is a highly well, I think we're kind of coming together on what we really think happened. But let's just put it this way: through most of the early 2000s into the 2010s, I'm going to say that this was a hot, it was a pretty hotly debated topic, and still is, um, because it wiped out, 95% of life. You know, we didn't have a smoking gun crater like we do for the Cretaceous. Of course, everybody immediately sort of went to that thing. So we really needed to come up with some other ideas in what was doing this, and it took a long time to do this because, you know, if you're not seeing, if it's not really visible, the cause, then you're going to have to start seeking it out through other, like, secondary means, like maybe taking chemistry of the soils at a particular time, or looking at the concentrations of fossils, like, from carbon, how much carbon was there at that particular time. There's ratios that we use. There's oxygen ratios. We can look at what the air was like. We can get a temperature of the earth. So we're using different things to find out what triggered this. And as it turns out, there's a lot of evidence out there, and now we have some good ideas. And really, what did this is quite simply, the beginning of this was the coming together of Pangaea. Pangaea came together in the late Carboniferous, early Permian, and when it did, it disrupted the world ocean flow, and it just had dire consequences on ocean flow circulation, causing one area to increasingly become stagnant, while another one upwells, bringing up acidic water, and all sorts of stuff. Because prior to Pangaea, when the continents are apart, the ocean just kind of flowed around, and when it flows around, it circulates, and things get moved, and things get stored, and things get released, and blah, blah, blah. But when you put a big dam in front of that ocean current on the equator, it really stops. It has really dire effects. And the only thing really up until the late Permian that kept everything in check was the Appalachian Mountains. The Appalachian Mountains, because the Appalachian Mountains were the size of the Himalayas and probably twice them, easily. And when you have a mountain range of that magnitude, on the equator, the weathering is just accelerated. And so what you have happening is you have CO2 being constantly be removed from the air by weathering processes. And when you have mountains, it just steals that CO2 as it weathers down, and then throws it into the streams, and then throws it into the soils, and throws it into the oceans. Well, you're going to be starting to put a lot of CO2 in that ocean. Problem is, if the ocean circulation is moving, that CO2 gets spread, the diatoms get it, they drop it to the bottom of the ocean, it gets stored there, it gets subducted, and everything keeps on rolling. Well, when you cut off the ocean circulation by putting, North America and Asia and Africa blocking the whole thing, well, that acid, carbonic acid coming off of the mountains is now going into an area of ocean that is no longer able to move through, and it starts acidifying that area of the ocean. And when you start acidifying the ocean, things it's snowballing, because now even the creatures can't pull out carbon because they can't precipitate shells because it's too acidic. So you get this runaway effect. And when you also block the circulation, things get stagnant, meaning you're not getting a lot of mixturing, and guess what? Things become anoxic. And then, when things aren't moving around and they're on the equator, they tend to get hotter. And as the temperature begins to rise, there's less oxygen. The ocean is unable to start turning over and turning over the oxygen. So now oxygen is being stagnated in upper levels and not getting below, and causing anoxic conditions. And that's bad for life. You cannot survive in that. And then you've got more carbonic acid putting in, but now there's no creatures to take it out. So that is one of the big problems that we have, is acidification of the oceans and anoxia. And the two go hand in hand. The more acidic those oceans get, the warmer they get, the less oxygen there is in there. Okay, so what likely didn't cause it? Impact. We're pretty sure, right? I'm not going to say for sure on anything because, not a fool. Could be anything, but most likely not impact. Possibilities, acidification of oceans, I just went over. Anoxia, large igneous province. That is the lips. That is the Siberian Traps, which I'm going to go into in great detail. So far, one of the largest known volcanic eruptions and flood basalts that we know of. And, you know, to put that in perspective, we had a fire, you know, Canadian forest fires. We get them every summer, you know, burning in Canada, you know, 100,000 miles away, whatever. It was enough to make the sun turn red for like, you know, 2 weeks. That is just a forest fire. The large igneous province of the Siberian Traps would have buried the entire area of Canada in under 200 meters. That's almost, what is that? So 2 times 3, 6. That's 600 feet of lava rock. I'm not talking Montreal. I'm not talking just Quebec. I'm talking the whole thing. The whole thing. They say if we put it in California, it'd be 2 miles. So, and it happened in a very short period of time, which means it absolutely choked the atmosphere and cooked the planet. So, anyway, so we know that that led to rapid climate change. Methane release, you know, that we're still trying to figure that one out. It's sort of, you know, it was one of those beloved darlings of the scientific world for a while there, but it sort of has subsided. I don't hear that much about it, although it could be a contribution. I don't know exactly how the methane releases go. Are they random? You know, methane may be built up. You know, the ocean was still trying to go east to west, so maybe against the east coast of Pangaea, you know, it just built up there, you know, and it just blobbed, you know, released. So ozone destruction, I'm not sure if that would be related to stardust or gamma ray burst, but it might even be the Siberian Traps. But ozone destruction can certainly cause problems. Stardust or nearby gamma ray burst, yeah, that could really, I'm not sure what the effects of that are going to be, but if it's strong enough, I mean, let's face it, everybody gets cancer, few survive. That's a possibility, but we don't really, I think you would see it. I don't know how you'd really be able to tell. There would have to be, I know what they use. They use this cosmic, something on rocks that they use. Like the outer layer of rocks gets beaten by cosmic rays, and there's a way to measure how long it's been exposed to cosmic rays. So I guess the problem would be, I guess you would have to find an actual layer of this at that exact time or shortly after and determine if there was an increase in cosmic rays. It's a pretty hard thing to figure out. But anyway, you know, good luck to that. And maybe all of the above, who knows? But those are sort of some suspects. So let's do the events leading up to the end Permian extinction. Prior to Pangaea, the Earth was cold. It had glaciers in the early Permian, meaning lots of oxygen, less carbon dioxide. Ocean circulation was effective, and waters maintained high levels of oxygen. Yay! Her life is thriving, and it was, man. It was really, it was. Permian life was as good as it is now in just one cycle earlier, if you really think about it. Carbon dioxide was kept in check since Pangaea came together in the late Carboniferous. Large mountains, i.e., the Appalachians, locked up CO2. Due to silicate weathering and kept, you know, a good amount of the carbonic acid out of the oceans. Now, Pangaea comes into focus around 300 million years ago. Pangaea interrupts ocean circulations. Oceans start becoming more anoxic. By late Permian, climate started warming rapidly due to the influx of CO2 to massive erosion, leveling of... See, now that the mountains get eroded, here's the problem. The mountains get eroded. Now there's no more... There isn't a giant sponge to soak up the CO2. So the CO2 is still there, but now it's not in check anymore because it's bombing down onto the rain is bombing down onto the surface. There's nothing to weather it out because it's all been eaten up. And now it's running heavily in the rivers and ending up in the ocean and really starting to acidify the oceans. And like I said earlier, when you acidify the oceans, you cause a snowball effect where you cannot... you end up having no means to transfer it to the bottom of the ocean where it gets stored, and you have no animals that can pull out carbon by itself because, let's face it, you need shelled organisms. If you want to know if something was a limestone, when we test it, we just take, is it a quartz or limestone? Well, we take acid and we drop it on and it fizzes. So, you know, there's areas in the world where you get upwelling that has lots of has acidic waters, and some areas the shells um, cannot precipitate. And there's a mineral called aragonite that is associated with sort of the comeback of this. I don't want to really go into it too much detail because I'd have to do a little more research on it, but I believe aragonite is sort of a high-end precipitate when the conditions are not ideal for calcium carbonate to be extracted. Um, so aragonite, yeah, there's another one of the atomic spots is being occupied by a different atom, and I'm not sure what it is. Argon, maybe? I don't know. Aragonite? No, it can't be argon. I don't know. I'd have to look that up. So, I never said I knew everything. Um, all right, so Pangaea drips, ocean circulation, and oceans start becoming anoxic. By late Permian, climate started wrapping risely, blah, blah, blah. We went through this. And with the leveling of the Pangaea Mountains, there's no more silicate weathering to lock up CO2, and plus also contributing to heavy rains and what have you is the geographic location of supercontinent in the equatorial area. With the Pangaea Mountains, i.e. the Appalachians eroded, carbonic acid begins to accumulate in oceans from rivers dumping more carbonic acid into them. Global temperatures begin to rise, causing more rain, accelerating erosion. Oceans become more anoxic, eventually becoming euxinic, and actually precipitating pyrite right out of the. So now there's no oxygen in there, and so sulfur combines with iron, and you get pyrite. So usually it combines with oxygen, but there's no more. So pyrite begins to precipitate out due to the lack of circulation and the mixing of deeper waters. Should be like a slash there. Sea levels fluctuate rapidly and generally drop, a worldwide regression. Temperatures spike near the end of the Permian, so everything just cools, but then at the very end it just rapidly cranks. So life is already stressed in the 10 million years approaching. So life, we had the shelves drain, causing major problems. There actually is a very big extinction event in the mid-Permian, probably related to that. And then, life kind of, inching along, and then all of a sudden, it's trying to get itself going, and it's used to a colder climate, and then everything just rockets. And again, with dire consequences. All right, so here's the culprit. Without a doubt, plays a significant role in the death of millions. Pangaea. And as I said, you have a current that wants to go this way, but now it cannot. So you have the sea in here, the Paleotethys Sea, and it is just getting stagnant, and you've got massive erosion going on right in here. You've got 25,000 mountains that are just right across the equator, and they are shedding and they are weathering and they're keeping everything in check for a while. But once these level down, all of this rains and stuff is going to start dumping heavily into here and making this area very acidic. And even worse, when you start blowing out, you have offshore currents more or less, you get cold upwelling. And you know what resides way down in there? Carbonic acid. And so now you start getting it over here as well, and it starts drifting. So the carbonic acid just becomes a huge problem. And we are putting carbonic acid in the oceans right now at an alarming rate. So, be warned. All right, the geologic carbon cycle. This is complex, and even I always have a rough time with it, but I'm just going to give you a layman's version of it. All right, so where do we start? You got the ocean here, you got a mid-ocean ridge here, you got a plate being subducted here. So let's start there. Plates being subducted, CO2 is being released into the water here through volcanic eruptions in the water, blah, blah, blah. The plate is being dragged underneath the continent, the oceanic plate. But as I said, carbonic acid is in this water, and there's little critters in here, diatoms, that take it and then they store it down here in the depths where it can't harm anybody, kind of like gluten. Put it all down here where it can't not hurt anybody. So you store it all down here, and it stays safe and away, and it's in the deep, and it eventually sort of gets absorbed into the sediments and what have you. And guess what? Those sediments get dragged right here, you can see it, and the carbonate just gets taken out and dumped and put into here and comes right back out in the form of volcanic degassing or outgassing. So carbonate sink, boom, dragged, melted, back up, goes all the CO2 back in the air, rain comes, CO2 and H2O form carbonic acid, the carbonic acid falls onto the mountains, and the mountains start to erode, and then the carbonic acid goes into the river, and then it gets put out into here. And then the carbonic acid goes right back down. It's also coming from here. And so basically, acid into the ocean, gets sucked out, sucked under the continent, blown out into the air, rain mixes with it, it drops in the form of rain, and then it breaks up again over mountains, and then gets stuck, so it goes whoop, whoop, whoop. That's how it goes, just like that. Any one of these, when you don't have a lot of volcanism, no big deal. There's not enough carbon, CO2 to do much. When you have a lot of volcanic activity, it becomes a problem unless you have high-rising mountains to take care of it. And not just the high-rising mountains, but you need an ocean that's capable of transporting it from the shallows to the depths in the form of diatoms. Any one of that cycle gets busted up, the whole thing goes haywire. Oh, and what we're doing is we're creating a problem where we're acidifying the oceans and warming them up, and the diatoms are dying off. As soon as these diatoms die off, we have no way to get rid of this CO2 and put it down in the sink, and this is going to start to rise. Nothing really lives down here. This is really it's sort of a death zone for many creatures. And if this starts to rise, and it becomes a point where they can't even live in it, it's going to start rising and rising, and the oceans become acidic. So when we are doing that right now, we are acidifying our oceans. And the diatoms, I guess I saw a thing where there's a picture of the 60s of the diatoms, coverage in plankton. And then there's one in the early 2000s, and they have reduced by, I don't know what the percentage is, but it's fairly alarming. It's very, very high in scientists. And the minute those guys are gone, we are in deep trouble. And I'll even further, we will be in deep shit. So remember that. All right. Pangaea paleoclimate. We got the Tethys Sea. It's being dammed up. We have ever wet tropics like right here. This would be like Nam, or just think of, it would look like the scene from The Predator or Platoon or any of that. Meanwhile, we've got huge mountain range. The lower mountains would look like the Amazon, just lush jungle, probably rivers just like the Amazon, gushing out all sorts of chocolate water. To the back ends here, you have desert. You have equatorial deserts, but then you get the temperate deserts, and of course you'll get a back area over here that's tropical wet as well, sort of like the the west coast of Africa, in the little dip right there, the little corner. So you're getting monsoons here, consistent rain here, massive erosion. Stuff is getting dumped in here, stuff is getting dumped in here. But what's worse is that these areas that were once lush and green, or just, savanna-like, we'll just say, with consistent temperatures when these were separated, are now not like that at all. They are becoming deserts, and they are becoming, the temperatures are starting to fluctuate between night and day. And that is a problem. If you're used to a nice, consistent temperature and things start fluctuating, well, you need to evolve. So you got your cold zones up here, you got your ice age down here, you got glaciers and stuff like that. So the world is changing. In the Carboniferous, it was beautiful and warm and wet and green, but in the end Permian, it has become a desert-like environment for the majority of the continent, or savanna. You've got your tropical areas, and then you got your cold and ice down here. You got glaciers down here. But this is no longer the Garden of Eden like it once was in the Carboniferous, in the early Carboniferous rather. And this is sort of where you would see, like I said, massive monsoon right here, massive monsoon areas. So you've got massive erosion right here, and then you've got things being spread out, and this is, this is going, this might be more monsoon, but this is going to be a consistent wetting effect. In other words, rain is just going to be constant right here. And then it's going to, your monsoon areas will be here and here. I kind of made this a little bit big, but you get the idea. This is just an area that just looks like Vietnam or any tropical jungle. And then here, and probably down in here, I should put another one. You're seeing areas that are just becoming, these are just deserts right in here. This is a colder desert, but you're still getting seasonal stuff here. Depending on, I'm sure in the summer and the winter, considering it's a supercontinent, you're going to go from very cold to very warm. You'll probably get some monsoon effects there. So, anyway. All right, so what's going on in the oceans? This is a big thing right here. This is a sort of a chart, bar chart of a variety of different things that we use to more or less gauge the health of the Earth, we'll just say. When you're in blue, everything's cool. That kind of goes nicely. And same here. Blue, healthy, calcium-based organisms are thriving, blah, 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 and everything's great. Now, as you move up, you begin to go into gray areas. Gray means that you have reduced oxygen. And when you have reduced oxygen, you're not getting the calcareous precipitate animals. You're just getting chert and siliceous chert. In other words, there's not really enough oxygen to produce a healthy amount of reefs and stuff, and all you're getting is spicules of chert. And all of a sudden the fossil record starts to show nothing but chert. And chert, for the most part, is indicative of a very, I don't want to say poor life, but there's not much life going on. There's no reef development or anything like that. That would be more or less where I'm at. And then of course you get to the absolute. This is the line in the sand where the extinction event happens. And when you go into black, it's bad. Like the black shales are indicative that there's anoxic, and nothing is really, it's not degrading. There's no light. Nothing's getting through, and anything that uses oxygen is gone. There's just no way for it to live because there's no sunlight that's going to get down into there. And this is basically just death. The black is like you are in bad shape, and it runs through all spectrums of our little charts, like black shales and poorly bioturbated. Yeah, here they are. Everything's great here and great here, but this is when they max. Evaporites, right? They become literally non-existent here. The pyrite begins to precipitate here, but then it cranks right here, telling us that we have literally no oxygen. I don't know what that does. Molybdenum, I'm not sure what that does. Not sure what that is. The oxygen, that's another one. That's just saying that when you're black, it's bad. But so basically, what you're looking at is a series of things that we use to gauge the health of the planet, and anything that's gray is probably 50. Let's just say that this is 50% and above, going great. This is 50% and below it, and getting in poor, and then in the black, you're approaching from like 10 to 0 on the chart. And 100's great, 0's bad, and you're in the single digits along right here. And what you see is the lead up here where things start to get bad progressively. Then they just absolutely get horrific. And then you can kind of see, like, and they stay horrific for, what is it, maybe, I don't know, 500,000 years maybe. And you can see them trying to jumpstart, like this, right? The evaporites took a long time to get going again. But you can see, where it starts to get gray again, things start to get better. And like here, you're showing jump starts. Starts, stops, starts, stops, starts, stops. And so it took life a little while, look. 248 from 252, that's almost 4 million years. So it took a little while to get things going again. All right, so here's another piece of the puzzle. So the Earth is basically in dire straits, and then all of a sudden this comes along. And I cannot reiterate this more. This can fill a good portion of North America over 500 feet deep of lava, okay? And it's a good chance that it's extended a lot further out. These mountains probably helped define it and confine it a little bit, but we know it banked up against the Urals, and it probably went down here somewhere. So what we see now, I would easily estimate it was twice the size at one point. And by that I also mean thickness and just materials. Materials have now been eroded, and deposited out here and stuff like that, and whatever, looks like the most of the watersheds here. Yeah. So, anyways, Siberian traps, bad stuff, happened, in a few million years, and absolutely, this right here, I have no problem believing that the Siberian traps probably filled all this out here, and that's why this is kind of the way it is. It may have been down pressed, but maybe this is even part of it. I don't know. I have to look at a Google Earth. But the Siberian traps erupted at 251.9, right at the extinction event where we see 95% of life just get whacked. So life was having a very hard time, and then this comes along, and this just does it. When you pump out this amount of CO2, and not to mention mercury. Oh, and the best part is this whole area, this whole area was a huge coal field. So it's like erupting a volcano and pushing it up through a ocean of gasoline. So the amount of dust that came out of this, and I mean, we have coal that's been on fire for like 200 years in West Virginia. We can't put it out. It just moves around underground in Pennsylvania. It's like these idiots that started this thing, it got out of control, and it's been burning, and so it's just burning underground for centuries. And that's an Appalachian coal field. They aren't that big, man. Like, seriously, like, it would be a pinprick in if you put it on the map of this. Having this erupt through the Carboniferous, the majority of our coal comes from the Carboniferous. So, yeah, we'd have so much more coal if this didn't happen. But this burned up through basically a reservoir of gasoline. So think about that for a minute and what that does to everybody's having a hard time. It's hard to put food on the table. The climate's going crazy. I can't precipitate a shell. And then this comes along and dumps massive amounts of carbon dioxide into the air, the water, anywhere you can think of. Carbon dioxide probably blocks out the sun periodically, so you might have some radical ups and downs in temperatures. So only the hardiest are going to make it. So Siberian Traps defined. Siberian Traps is a large region of volcanic rock known as a large igneous province, a lip in Siberia, Russia. The massive eruptive event that formed the traps is one of the largest known volcanic events in the last 500 million years. The eruptions continued for roughly 2 million years and spanned the Permian Triassic boundary, or the PT boundary, which occurred 251.9 million years ago. The traps are believed to be the primary cause of the Permian Triassic extinction event, the most severe extinction event in the geologic record. Subsequent periods of Siberian trap activity have been linked to a number of smaller biotic crises, including the Smithian, oh yeah, I'm not even trying to pronounce all these, extinct. They're just smaller time period extents. Large volumes of basaltic lava covered a large expanse of Siberia in a flood basalt event. Today, the area is covered by about 3 million square kilometers of basaltic rock. It's 7 million square miles that consist of 3 million square, 7 million kilometers, which is 3 million square miles. Yes, square kilometers, square miles, yeah. Of basaltic rock with a volume of around 4 million cubic kilometers, or 1 million cubic miles. So estimated to have covered the entire U.S. and around 200 meters of rock, and also a good portion of Canada. A majority of materials erupted in less than 1 million years. Wow. So it's too bad most people don't remember what St. Helens did, but that was just, again, a pinprick of what this thing did. If we had this happen now, we'd be dead. Humans would probably make it, but I would say 80 to 90% of us would be gone, and gone very quickly. All right, here's a cross section of the traps. So right here, nothing, right? Else peaceful. So you get your first kind of pops in sort of clearing the conduit, as we'll put it, and you get a nice little dome that comes out. And as the loading of the dome comes, you're kind of depressing the crust, which is in response forcing more stuff to come out. So as time goes on, these as this presses down, it needs to keep going out further and further because this keeps gaining mass and harder to punch through. Well, the surrounding areas are all coal fields. So as you're going out horizontally, you are just ripping through you know coal fields, and the further you go, the more coal you burn, and then it burns underneath and causes all sorts of crazy problems underground. I would imagine the gas emissions are just off the charts, and over time, this network of dikes and sills and stuff just keeps networking out, and it creates this just giant area of burning gaseous lava flows. It probably just, if you imagine what everything Hades looked like, or hell, that's probably what it looks like, man. It would just be awful. It was just scarred and black, black surface, probably cloudy, dusty, sulfuric rain. I mean, just a complete nightmare. So, stage one is the building of it. Stage two is really the extension, the conduit, the formation of the plumbing system, and then by stage three, you're getting periodic pulses, but everything's kind of starting to calm down, calm down, and it's basically going to work its way to where it finally just stops. That's the thing about flood basalt. It kind of happens in one area, and once it's done, it's done. So down here you've got sort of an overview, and you can see lavas here and pyroclastic rocks and sills, and it just gives you an area of how spread out this thing is. This is like 500 kilometers. I mean, this is one little area. It's crazy what this did. So anyways, that's sort of how it worked. Effects of the Siberian Traps. Now, take into account the climate of the Earth was already stressing life forms. They released massive amounts of SO2 and CO2 in a short time, creating a seesaw effect of global climate. SO2 reflects. It generally cools things, very quickly, but it gets out of the atmosphere quicker. So CO2 sticks around more, and so you get the SO2 fluctuation, the dip, and then the CO2 comes along and just continually warms things. And then you get another blast of SO2, and there's a quick dip, and then it just continues on. Likely blocked out sunlight numerous times, slowing or halting photosynthesis worldwide. And without photosynthesis, you're not taking away any CO2. Accelerated acidification. This leads to acceleration of acidification of the oceans, as well as anoxic emissions in the ocean. Massive release of toxic chemicals, especially mercury. And this was really concluded. I mean, not just the rocks, but there was a guy that I watched this lecture, and he does nothing but, I believe he's in Canada, and his whole life, I mean, his career is looking at the dust that comes out of coal plants. And when he looked at some of the dust that was collected at the Permian Extinction from the Siberian Traps, he found them to be almost identical. He goes, you have just basically, coal dust that's coming out, and it's toxic, and it's loaded with mercury, just like the stuff, it's like mercury for life forms is absolutely, it's just no good. I mean, the fact that my grandmother used to play with it in science class, and when I'm in my 50s, and we looked at it, but we weren't allowed to play with it because mercury is the only metal that's liquid at 1 atm, and basically the temperatures that we are able to survive in. So don't play with mercury. Eventually set global temperatures, possibly the highest ever seen on Earth. Worse, the Siberian Traps erupted in a giant coal field that was created in the Carboniferous, making all the above orders of magnitude larger due to forest fires. The climate was driven to a dry, barren landscape, and the ocean barely able to host life, close to a 95% fatality rate. It was no joke. All right, so here's what it kind of looked like. So we're down here, everything's wonderful. You got trees, you got a nice pond, you got some mountains right here, and yay, everything's good. Life is flourishing. Wow. We get into the extinction event, the EPME, early in Permian, what is it? Terrestrial EPME, early Permian mass extinction interval. And this is now erupting gas and polluting the air. You've got global warming. Trees have been killed, so they're not breathing any carbon dioxide. You've acidified and destroyed the pond, the lake or whatever. It's kind of probably, representative of the ocean. And there are wildfires burning everywhere. So everything's scorched. It looks like any forest fire you've ever seen. And then after 4 or 5 million years, life starts to make a comeback. These have calmed down. And you're starting to see the Earth reemerge. It was once a lush tropical green place, and what follows is basically a savanna-like desert that lasts for a very long time. And when I say a very long time, we're talking tens of millions of years before it really starts to get going again. But this area right here in the Lake Carboniferous, the Permian, nice and warm and consistent. Reptiles and amphibians love this. Only reptiles can survive in this kind of stuff. When you have much cooler temperatures, you have very little water, and the water, this was all polluted. The reptile is now about to take control because it's the one thing that can handle being, dry. And it also, the land-dwelling reptiles also, they're able to move around more. So anything that was slow and sluggish, amphibian life down here, just got wasted. And it's things that were small. It was things that could hide. It was things that could survive off very little. And so you have a whole new set of species that are very thin and they're just nimble as hell. You don't see a lot of big creatures in the early Triassic. Everything's just starting out small. And the first mammals show up. And guess what? Why? That reptile decided to make one more step of evolution and keep itself warm. And this is probably one of the big reasons why they survive. They start to show up here, and really it was the lineage of the Gorgonopsids and what have you, that whatever. Obviously they didn't make it, but our relatives that were smaller versions of smaller species of mammals. They were able to basically regulate their temperature somehow, or their start to, and of course, I'm not sure if hair actually shows up at this point, but they are able to regulate, and they live in burrows, and they are basically in hiding for the next 170 million years. But whatever happened through here, whatever mammal or small mammal that was in our lineage somehow was able to leapfrog through this and managed to survive. And then the brave new world here is much different. It's dry, it's cold, and everything is very quick. So being small and able to hide and regulate your blood temperature is going to give you an advantage. However, it's really a race between you and the traditional reptile. At this point, the traditional reptile, because it is still fairly warm, it still has the advantage because he's more evolved and a little bit bigger, and it's developed some what's the word I'm looking for? Instinctual skills that are these ones just the early mammals really have not. So reptiles take off. They can handle the dryness. The mammal's going to still need more water. It's going to need more energy. So there's just not a lot of food, not a lot of water. So it's the reptile that can survive off of a minimal food. Like alligators sometimes don't eat for months. I think I've heard about that, or snakes or whatever. And they don't need a lot of water. Now a cheetah needs let's just say that this was the amount of food an alligator needed to survive for a month. Well, that cheetah would need 1, 2, 3, 4, probably 12 times that. And you can apply that to water too. So with a barren earth, the mammal survives and is doing okay, but it's the reptile that needs less energy to survive, and it takes off, and i.e. we evolve into the dinosaurs. But as we all know, they get their time coming too. And as Clint Eastwood says, we all got it coming to us one day, kid. Sobering thought. In summary, the end Permian extinction is the largest known of its kind, greater than 90%, and occurred roughly at 251.9, but we'll say 252. Although the event appears almost instantaneous on geologic record, however, it may have started up 10 million years prior. Life flourished for most of the Permian period, and almost all niches were occupied as they are today. Just picture a sort of a savanna life, just lions, tigers, bears, you got giraffe, gazelles, you know, they've all of those represented. And plus you had your lizards, your crocs, all that stuff. Frog, turtle. When do turtles show up? I don't think they show up till later. Anyway, Permian period started cool with glaciations over Gondwana, South Pole, but temperatures began to rise and glaciers melted. As Pangaea came together, a giant mountain range, i.e. the Appalachians, occupied a large area near the equator. This kept carbon levels in check and kept them low and temps cool. As the central Pangaea Mountains, the Appalachians, eroded, less carbon was locked up due to silica weathering and now pouring into the oceans. Oceans became more acidic and global temperatures also started to rise. Also due to the melting of the glaciers over Gondwana, and plus the locking of the cutting off of the world oceans. As global temperatures rose, ocean temperatures rose, causing oceans to become more anoxic and even acidic in some places. Again, able to precipitate pyrite from seawater, iron, and I believe sulfur. Due to oceans, again, you got sulfur going in the water. Due to oceans becoming both acidic and oxic, sulfur, by the way, is related to the volcanism. Life began to struggle, and even worse, sea levels dropped worldwide, stressing life on the continental shelves. So, you live on the continental shelf, if it dries, and believe me, tons of stuff likes to live there, and if it dries out, you need to either adapt or die. Summary continued. As the Pangaea supercontinent took shape, the climate went from relatively stable and ocean-influenced to land-influenced, typo, in many places. The climate began to have major seasonal fluctuations, stormier weather patterns, and large desert areas forming. Due to the central Pangaea Mountains being located near the equator, monsoon seasons caused massive amounts of sediments to be deposited into the Tet Sea, pushing oxygen levels lower. That's due to visibility and just choking up the water. Think of Willy Wonka, the chocolate water. Think of the Amazon dumping. That you've never seen a clear Amazon River picture. It's just you can't see your finger under the water. Overall temperatures began to rise rapidly near the end of the Permian. Life is now very stressed. And then, drum roll please, dun dun dun. Siberian Traps erupted in late Permian, dumping massive amounts of SO2 and CO2 in the atmosphere, causing huge fluctuations in global temperatures. The Siberian Traps are the largest known volcanic eruptions to have occurred. It's not in geologic time, it's in the last 500 million years. That's the error on my part. There are other ones that are certainly bigger. With an estimated amount to bury the U.S. by 200 meters or 500 feet, well, 600. They released massive amounts of toxin, most notably mercury, and this had a huge effect on life. They also ignited the coal fields in which they erupted in, which were of similar size. The end result was a global climate went from a wet, stable environment to a hot, dry, barren, unstable environment less than a few million years with equally polluted oceans. And guess what loves hot, dry climates? Reptiles. And guess what? We are going to move into the dinosaurs. What was the likely cause of the Great Dying? You guessed it, Pangaea. Plus, with a nice smack around from the Siberian Traps. All right, so state of the Earth from deep underground to the atmosphere 300 to 200 million years ago. This says it all. Everything was great, and then everything is back. Well, different, but that's about as good as you're going to get. Hold on just one second. Apologies, I had to check the fire because it is cold. 27 right now, but it's going to get a lot worse. Okay, so state of the Earth from deep underground to the atmosphere from 300 to 200 million years. Great chart. So, mantle convection. Continents converging. Pangaea takes shape. Pangaea rifting. So, up until they actually come together, you have world circulation. Once Pangaea comes, you've got, what, 265 to we'll just say 230, 240. So that's what, 25 million years of just basically nothing getting through. The core wandering the geoid. I'm not exactly sure what this means because you have a Paleozoic geoid and then Mesozoic geoid, but what does that mean? And there's something called transitional in here. So So you have a carbon reversed supercraton, Permian Triassic mixed supercraton, and then you have a Triassic normal supercron. I don't know what that is. Oh, that's a magnetic field. Okay, so that's the magnetic field. Now you have morbs being erupted, and then you have massive flood basalts, and then morbs. So this is basically showing volcanism going on a decline right here, as you're coming up to the to Pangaea, because once the Pangaea comes together, the mid-ocean ridges really stop firing because there's no place to push anything, and then everything kind of just stays mellow for a while, which probably is maybe one of the causes that the Siberian Traps, there just was no release of heat. And there's also another one right here. And then the mid-ocean ridge system begins to accelerate very quickly as Pangaea breaks up. So seawater coverage, this is basically, so you see a very high level of sea level. And then, of course, it bounces around, but it's generally on a trend lower, and then it just goes way down right here. And then it fires back up. So this, I mean, anytime you have something like this is just going to cause a lot of problems. And then, of course, it stumbles along, and it kind of reaches a peak up here before it starts declining again, and then it actually goes back up again. But that's off the maps. So the Earth's surface system, so this is basically seawater coverage on the shelves. So it's not seawater coverage worldwide, this is seawater coverage on the shelves. That's what this means. So, 30% of shelves being covered is pretty good. Less than 10 is really bad. Carbon circle. So, this is basically saying that whenever the this carbon ratio is high, you got good life. When it plummets, it means that there's not a lot of living stuff going on. So you had a huge drop, it rebounded, drop, and this is life trying to get its act going again, and then it kicks up, and then it starts taking off again. But as you can see, this is just showing you're having massive fluctuations in carbon production, which means that life is really having a hard time. And right here, it's got to go negative. That's the great dying right there. All right, so the ocean. What's the ocean doing? Well, oh yeah, this is the aragonite. That's what I was talking about. So you'll get things that will start precipitating aragonite on the edges of that before you start going into full calcium carbonate production. So you're seeing the line here, and this is the anoxic and oxic. So plenty of oxygen, boom, all the way into the negative. This is when you're precipitating pyrite and all that stuff. And then you're getting life is trying to get going. It gets oxic again, and then boom, it plummets. And again, it's this is life trying to start again, and because when life gets going, it basically starts to essentially heal the oceans, but then it falters. And these are probably, they may even been like sporadic eruptions that just kept going from the Siberian. I would have a feeling that the Siberian Traps are related to these, just further eruptions in time down the line that is causing this. And I'm not really sure when this gets precipitated, but maybe this is the line right here when you're actually doing aragonite. I'm not sure what that exactly. So here's the climate, warm to cold. It was cool, glaciers, as I said, and then it just absolutely cranks. You've got, according to this, you have a methane release right in here, so I guess something was released. Whether or not it caused it, I don't know. But this is just basically the temperature dropping, the temperature cooling. This is the temperature warming, and then the temperature cooling back down, and of course there's a spike right there. Biodiversity, lots of different critters in action around. Boom, crashes. That's the death sentence right there. That is the extinction event. And then of course it wobbles a little bit and fumbles, but then it gets going again. So, and then of course, as you go further up, there'll be a couple more extinction events. But that's the state of the Earth from the interior to the atmosphere. And again, I apologize. I do not know what the difference here is about Paleozoic and, well, I guess one could say that when things were coming together, the Earth would spin a little bit. The shape of the Earth would be a bit different, as opposed to when you go into the Mesozoic and things start breaking up into different areas. So this is basically saying that the Paleozoic had a certain shape to it. And then in between the Paleozoic and the Mesozoic, for a period of time, you're going through a transition cycle. And of course, it's very much related to where Pangaea coming together and Pangaea separating. So I don't know what this is. This is a magnetic field. Now the magnetic field can do. I would have a feeling that the magnetic field would change depending if there's a supercontinent. What exactly it does? Well, this is a reversal right here. So we know that the magnetic polarity in the Earth switches periodically, and this must have been one of them right here. And has it been linked to mass extinctions? It's pretty suspect at this point, but it certainly doesn't help. A lot of things are in tune to the magnetic field. It's how birds, from what I understand, it's how they find their way. I believe lobsters running across the ocean. I mean, think about it. You've got blood, you have iron, so you're in tune to the magnetic field of the Earth. So if it starts switching on you, well, you might not make it to where you're supposed to go if you've been using it as a guide. Global temperatures and CO2 levels over the past 600 million years. This is sort of the average global temperature right here, and it kind of stays stable. Bloom, you get a plop again, mass extinction right here, and then in Devonian you get a drop, another mass extinction here, and then you get a severe drop right here. But ironically enough, no mass extinction, and it's not until you come back up very quickly that you get a nasty one right here. That's the Permian, and that's the temperature's higher than it's ever been at this point, and then it kind of plateaus off, drops in the Jurassic again, and then stays fairly level during the Cretaceous, and then after the Cretaceous and the Tertiary, it drops to where, like right now, we're kind of in a semi-ice age, because we obviously have Antarctica is obviously glaciated, and Greenland. So it's interglacial, but it's still glacial. We're actually colder than for most of Earth history. So CO2 amounts, man, you're up here at 7,000 ppm. We're down here right now at like 440. I couldn't even imagine what this would do, and it has been on a steady decline. And really, it's no. I mean, you're not really. It's not real surprise, because this sort of culminates when when you have things that start to breathe CO2, and that would be the plants. Now, I don't know what the cause of the drop is here, or the spike, but right here, I mean, this is when the plants really start to show up, and so this could be related to plants. I don't know. The Ordovician is sort of, I don't know, but we know that this is when they kind of start getting going in the Silurian. So anyway, this is basically telling you this is the Paleozoic life forms. You have the dinosaurs in the Mesozoic, and then of course the time of the mammals. Oh, and I love this. Plants and invertebrates, several mass extinctions, 95%, probably due to climate change. Well, see? All right, so Pangaea around 251 with Siberian Traps shown. These are the traps up here, kind of ironically enough in the same location that they are today. Had that happened down here, I don't know what would have happened. You had the Appalachian Mountains right here called the Central Period. You had deserts here and here, you got massive amounts of weathering right in here. These are the lees of the winds, the trades throwing the moisture. So you've got all this erosion pouring stuff into here, and that's what's choking up the sea. So that's just basically the geography at the extinction event. Evolution. All right, so this is a good one. This is going to show us, this is the lineage of how we ended up moving past the Permian Extinction Event. Everything here, mammals, birds, crocs, totars, snakes, lizards, turtles, the whole 9 yards, we are all related to this guy right here. And I can keep going back and bring you further back to where we really start, but that's for another discussion. In any case, this guy at about 300 million years ago, and the Carboniferous branched. And you had synapsids, which is us, and saurapsids, think of dinosaur, as um, as the uh, as the reptile version of it, or the reptiles we see today. We are reptiles. We're just a different form. So you have the common ancestor reptile right here. Went extinct. We branched off, and the mammal lineage went this way. The lizard lineage went this way, and the sauropsids. The difference between the two of these is really comes down to teeth, and this is just all I know at this point. Teeth and skull pieces and holes in the skull. I believe these guys have 2, but we have 3. We have 3 openings on each side. And that's, I guess, how they classify. Also, reptiles have 3.5 chambered hearts. We have 4. So, a couple differences right there. So anyways, sauropsids take off, and we all come up to the Permian Extinction Event, and we all pass through. But right before that, they go. These sauropsids branch off again about 300 and about 200 and we'll say 280, 290 million years ago. The sauropsids branched, and you got turtles, which became their own thing. So that's when the turtles were. They were in the Permian. And then the sauropsids go off on another lineage, and one of them has branches off to what's going to become the lineage of the dinosaurs. And this guy goes up and again branches, and one goes to the crocodiles, and one goes to the theropods, which is meat-eating dinosaurs. And the meat-eating dinosaur lineage actually evolves to what we say. So what a tyrannosaur is today is a goddamn bird. I mean, we all know that now, thanks to Jurassic Park. But I mean, you really can take a good look at a turkey or rooster. I don't care what it is. It's harder to see with the flying reptile, the flying birds. But these things have legs that look just like this. The feet are very similar, and they're bipedal, right? There's really nothing else besides humans, kangaroos, that really are bipedal. But the dinosaurs, most meat-eating dinosaurs, most certainly were. They were bipedal. All right, we can make an argument the Spinosaurus wasn't bipedal, but the Spinosaurus had much larger back legs than it did front legs. Anyway, so the dinosaur lineage goes here, and of course this branches off into a whole bunch of different areas. So you got lizard-hipped and bird-hipped and what have you. Anyway, actually, their lineage is right here. It's kind of on the crocodile lineage. Anyway, so the crocodiles just go to crocodiles. Further up, there's another branch where you get taras, and then further up you get lizards and snakes, right? I shouldn't have used that as lizards as a general. Lizard is just, it's a particular type, I guess, a branch rather of the reptile. So not all of these are lizards. Lizards are lizards, but all of these are reptiles, including us. Now we end up breaking off at 300, and we go over to here, and these are the Dimetrodons. This is one of our earliest successful larger relatives, and again, they had teeth that were there was at least 3 different kind of teeth plus canines in here, which is very mammalian. They had an extra socket for in the skull, the same amount, I believe, of plates that we have. I'm not 100% about that. And it was regulating its temperature. This is a big thing right here. Now, people have been arguing about this for years. I am certain, well, that's a powerful word, but I'm 90% plus confident that this thing was used to regulate its temperature. It was one of the first ways to do it. And the way it did it is, my theory is that, if you're living in a desert, the deserts are hot during the day, cold at night. Now, at noontime, when this guy's cruising around, it doesn't need to be heated up. So basically having the sails straight up and down really makes sense. And when the sun's lower in the sky, it's going to start heating. It's going to want to get warmed in the morning, and it's going to want to get heated in the evening before the sun sets. And I think that this design solves both those problems, and it probably helped in intimidation and mating and stuff. Big fin shows you're probably pretty healthy. So these guys are starting to regulate. Then you move up. The Theropsids were probably on the same path. They were able to have a metabolism that stayed relatively regulated. We're not 100%, but these guys look just like lizard lions. And of course the mammals. So that's the very simple animal evolution. We are all reptiles. which the reptile came um, from the amphibian, and the amphibian came from the lungfish, and so forth. So anyway, just another little chart of animal. Oh yeah, this is how you really. Okay, so our very first ancestor was an ancestral chordate. Chordate means you have a spine or backbone, a vertebrae rather. And even though the vertebrae isn't quite developed yet on some of these, there is a nerve cord that is, and that's sort of, I believe, yeah, chordates. Yeah, ancestral vertebrates. Okay, here we go. So yeah, chordate, I believe, has a nerve. Although I'm not really sure what that is. I might tunicates. Not really sure what that is. But in any case, yeah, this is the lineage of vertebrates. So we have yeah, lancelets. You got jawless fishes. Again, that's along our lineage. The cartilage fishes is along our lineage. The bony fish, the amphibians, the reptiles, and eventually us. So I'm not 100% if that applies to this, but I thought chordate, again, biologist, I'm not a biologist, I'm a geologist. However, we should know our paleontology, which means, that's study of ancient life. I'm just not 100%. I believe chordate does mean you have some sort of nerve, spinal nerve. So anyways, don't take that as 100%, but I think if I was going to make the $1 million guess, that's what it is. All right. This is just another chart, a little fun chart you might see, kind of help. I mean, I think of these as kids diagrams because it kind of jumps out, but it's good for adults. So this is showing the mass extinctions, the timeline, the periods, Mesozoic, Cenozoic, Paleozoic. This is showing, what was really killing it at that time, or killing it, I mean, like was living. So during the Archean, this is when life, this is a very single cell life. In the Proterozoic, we went from single cell or prokaryotes, cells without a nucleus, to eukaryotes. We are eukaryotes. To cells that had nucleuses, which gave birth to the blue algae, the bacteria, and the jellyfish. And then, of course, we get the invertebrate animals, brachiopods, and then we start really moving up the chain of life. And Paleozoic means life. And you can see here, this is sort of just showing you, this was life then. You got your trilobites, your ammonite, sea scorpion. You got your amphibians coming out here. Trees. This is like plants, trees, sponges maybe, jellyfish. No, jellyfish would have been way down here. I'm not sure what those are. Corals. Oh, echinoderms. All right. Anyways, age of insects in the Carboniferous because there's so much oxygen in the air. You got your Gorgonopsids. This is the mammal's peak, the reptilian mammal peak before it gets. This is like the lion, the lion reptile. This is kind of out of sync, by the way. This should be here and this should be here. These are some of the first, I think ferns. Ferns. I don't know what that is. Then of course the ancestral dinosaur. You have the dinosaurs evolving into birds. And of course, the mammals show up here, but then they really start taking off in the tertiary, the age of mammals, and here we are. So, anyways, these should be right here, and that should be there, but that's neither here nor there. This is the crazy. I mean, it gets nuts when you start looking at really huge ones. But if I was going to do this, I could chase this right up to here. So you got the origin of life. We go up through here. This is like, algae, bacteria, blah, blah, blah. And then we branch to here. Yep, then the fungus takes off right here. We branch here. We go up through here. Oh, yeah. So somewhere we get the common ancestor. Is it the chordate? I don't know. But then we branch off to these fish. Lungfish. Oh, I forget the name of that. And this is really these are your true fish. This is a plated armored fish. This guy was badass. You got the cartilage fish, sharks, rays. Then you're getting into you're getting into things that become more. They're starting to, like, these fins are starting to get sort of limbs to them, and now we're starting to see a fish-like creature that's changing its fins into something that looks more like an appendage, like a small arm or It's just not. It's able to move on land. Okay, so fin-ish, but this definitely looks like something that could crawl around on land. Then you've got, you go off to your snakes and stuff like that, frogs, turtles. This goes off into the dinosaur world. And then we break off, and the rodents, other male bats, horses, all that, and of course we're up here. So this is really it's a great artist concept of the tree of life. And believe me, it's way more complicated than that. That was that thing right there that I was looking at. What is it? It must be a sponge. I'm going to go sponge. All right. We have now entered the Triassic period, and I am going to end it there. I want to thank everybody for watching. And the Triassic we're going to move into the age of the dinosaurs, one of my favorite discussions. And that will be part 7. And again, thank you for watching. And there's Bella. When you see Bella, you know the lecture's done. Aloha and have a good night.